Hey guys, this is the part 3 of Redox Reactions, chapter 16, and we're going to talk about electrochemical cells. Alright, so before we get to the actual cells, we need to be able to predict whether it's going to be a galvanic cell or an electrolytic cell. And part of that has to do with the spontaneity, so whether or not something is spontaneous reaction. So here's an activity series, and an activity series shows exactly what it says. It shows how active those metals are. So in this activity series, they're listed in decreasing order of ability to lose electrons. So the ones at the top will react like this very readily. So lithium and potassium and calcium and sodium and magnesium, all those metals really lose electrons really easily, and so they get oxidized easily. Whereas the ones on the bottom don't really get oxidized very easily, but they would get reduced easily because they don't like to be oxidized. So the metals at the top of the list have the greatest tendency to lose electrons, so they get oxidized easily, and so therefore they're the most reactive, written like this, written as where they're losing electrons. The metals at the bottom of the list have a lowest tendency to lose electrons, and so they're the most difficult to oxidize and therefore the least reactive, written like this. If it was reversed and you were looking at reduction reactions, reduction half reactions, then the ones on the bottom would be the most reactive, if that makes sense. So if it was written with this being the reactant and this being the product, then this would be at the very top because it doesn't like to be oxidized. It would rather be reduced. Okay, so when is a reaction spontaneous? The reaction is spontaneous when you have the most reactive written as an oxidized reaction and the least reactive written as the reduced reaction. So if we have it written like this, where magnesium is going to magnesium 2+ and being oxidized, it has to be higher up on that activity series than the copper being reduced. So copper being oxidized is down here, while magnesium is up on the top. And so since magnesium is written this way in the chemical reaction, and copper 2 is being reduced, and it's written on the bottom, then this would be spontaneous. So this is a picture of copper solution. So it starts off as copper 2, and a magnesium strip being put into a beaker of that, and you can see the reaction takes place. The blue color, or the copper ions, is starting to go away, and we see this black stuff forming on top of magnesium. That would be copper solid, so the brownish orangish copper depositing on top of the magnesium, and the magnesium is dissolving and going into the solution. Now if we reverse that and we start off with copper solid and magnesium solution, nothing happens because we've got it reversed. We're trying to oxidize copper and reduce magnesium, and that's just not going to happen because magnesium wants to be oxidized. So predicting whether a metal will dissolve in acid, if I go back and I look at my activity series here, here is H+, right here. So as long as the metal is above hydrogen, then it would dissolve. So here we have zinc, solid, being put in acid, and we're forming zinc ions and hydrogen gas. And that's what these little bubbles are right here. They're hydrogen gas forming in the solution. And so if we go back and we look at the activity series, zinc is right here, and H2 is right here. So H2, this reaction would rather be reduced, and so it's putting H2, or the H+, in as a reactant. So it gets flipped. And then it also says an important exception to this rule is nitric acid, which through a different reduction half reaction dissolves some of the metals below H2. And that's because of the nitrate. It can do other reduction half reactions, and so it's a little bit different. But you're not going to have to look at that. All right, so batteries. Using chemistry to generate electricity. So electrical current is the flow of electrical charge. So in the picture, we have a copper wire and electrons are traveling across it, and that creates a current. Since redox reactions involve the transfer of electrons from one species to another, they can create electrical currents. So if we look at that, we get a voltaic cell, or It's also known as a galvanic cell. It's the same thing. I hear this way more nowadays than I hear this. Okay, but this is basically what a battery is, and we're not going to look at the details of a battery. If you'd like to, there's plenty of them in your textbook. We're only going to look at it like this, because you can really see what's going on. But galvanic cells are a type of electrochemical cell that create electrical current from spontaneous reactions. So these create a current because we can transfer those electrons that are being transferred from one half reaction to another half reaction through a wire if we separate the half reactions. So here we have the zinc copper galvanic cell. And so the overall reaction for this would be zinc plus copper 2 goes to zinc 2 plus copper. So here's the oxidation half reaction, and basically what we've done is we took a solid zinc strip of metal and we placed it into a beaker that contained zinc nitrate. And all nitrates are always soluble, so really what that has in there are the zinc ions. And then on the other side, where the reduction half reaction is taking place, we have a copper piece of metal that is put into a solution of copper nitrate, which basically has copper ions in it. We attach those two strips of metal with a wire, and we hook it up to a light bulb if we're just wanting to show that electrical current is passing through it, or you can hook it up to a voltmeter. You'll see that in the lab that you do, and you can measure the voltage that's occurring there. Now we have a salt bridge that's in the middle, and the purpose of the salt bridge is to complete the circuit. So what that means is whenever these atoms of zinc come off and go into the solution, so this would dissolve over here on this left side, the electrons then are ejected and go up here, because remember, this is the half reaction that's taking place. So we have zinc solid atoms going to zinc ions plus 2 electrons. So those electrons get ejected and travel up this wire. Now they're starting to come down on the other side. And so the electrons then come down here and they attach to a copper ion, and then the copper deposits on top of that electrode. And so over here we'll be gaining mass, while over here we're losing mass. Now, if the electrons are leaving this side and they're coming over here, that means that we're gaining positive charge here. So tons of positive charge is building up in this side, and tons of negative charge is building up in this side. So the negative ion in the salt bridge, so basically all it is a piece of cotton or something that kind of resembles cotton, glass wool is what's usually used, and it's soaked in a ionic solution. A lot of the time it's potassium nitrate. So we have the potassium nitrate in there. And the negative ions will travel down this way to neutralize all that built up positive charge. And the positive ions will come down this way to neutralize all the negative charge. Because remember, what we're doing is we're losing positive ions over here, and we're gaining positive ions over here. So we have to make sure that those charges stay constant, or the battery, the galvanic cell, would just die after one transfer. So the electrons here that are flowing across the wire constitute an electrical current, and it lights up the light bulb. So a closer look at the voltaic cell. Wherever the oxidation half reaction occurs, we call that electrode the anode. So that's the negatively charged side, and that's why electrons get pushed away from that. And then over here is the cathode, where the reduction half reaction takes place. And it would be positively charged, and that's why electrons are going towards that side. So on the anode side is where oxidation takes place. Anode is oxidation. They both start with vowels. That's how I always remembered it. And the prefix "an" means negative, like anion. And then we have the cathode is where the reduction side is. And it's positive, just like a cation. All right, so non-spontaneous reaction does not produce a current. So the voltage of a voltaic cell depends on the relative tendencies of reactants to undergo oxidation and reduction. So if it's spontaneous, meaning if the oxidation half reaction is higher on your activity series than your reduction half reaction, then the reaction would produce a current and it would be spontaneous and it would take place and you could set it up as a galvanic cell. So it says, combining the oxidation of a metal on the activity series with the reduction of a metal ion above it on the activity series does not produce a voltaic cell at all. So that would be non-spontaneous. But if you combine the oxidation of a metal on the activity series with the reduction of a metal ion just below it, results in a voltaic cell with a relatively low voltage because they're very close together. But if you separate those two a lot, you'll get a higher voltage. So you cannot make a voltaic cell by trying to oxidize copper and reduce lithium. Remember, lithium is one of those main group metals, and all the main group metals were up on top of the activity series. So this would have to be written like this. Whereas if that's going to react with lithium, it has to be in this form. So a dead voltaic cell, what happens when your battery dies is while all of these are turning into zinc ions, that's being eaten away. And copper ions are going towards the electrode. And so if you run out of those ions in the solution, your battery will die. If you run out of the electrode, the zinc electrode, your battery will die. Electrolysis. Okay, so electrolysis is the second type of electrochemical cell, and it is the complete opposite of a galvanic cell. So an electrolytic cell is what we call when it's a non-spontaneous reaction. So instead of generating electricity, these require electricity to take place. There's a couple of different ways you've seen this in real life. You've probably never seen it happen, but you've seen the result of them. So let's take a look at it. So the first one is when we talk about fuel cells. So fuel cells use hydrogen. And so where are we going to get that from? So we could take a solar or wind powered electrolytic cell, and that can be used to make hydrogen from water. So here's an electrolytic cell where we've applied a battery to it because it has to get electricity into it. So we could use wind electricity or solar electricity to do that. And we get on this side, and it's just placed in a water. We take the electrical wire from the battery and we place it in water. And then from that, we generate H2 and O2. And this side is going to be the H2, and this side is going to be the O2. And I know that from gas laws. We're going to generate twice as much H2 as we do O2 to balance the equation. So this one has to be H2 because there's twice as much there. But anyways, that's an electrolytic cell. Water doesn't do that on its own. We have to put electricity in to get it to work. And then down here at the bottom is an example of electroplating, or when they've plated other metals. So if you've ever bought jewelry that looked silver, and then after a few weeks of wearing it, it turns your finger green or something like that. It starts to change colors, not turn black because silver does oxidize. But you start to see that there's different color underneath. And that's because they use a current source and they put your object to be plated into a silver solution. And when they turn on the electricity from that, the silver ions then plate on top of the other metal object, whatever it happens to be. And so you then get the silver atoms to deposit on top of it, and then it's silver plated. So anytime something is silver plated, that's how they've done it. And so remember, these electrolytic cells are non-spontaneous. They would not produce electricity on their own, but if we apply electricity to them, then they will form. And that's all you have to know about an electrolytic cell. You only have to know that they only take place when electricity is added to them.